transformation. Laplace transform. Laplace transformation is key in engineering and sciences. Although this is the second phase of Laplace transform, Laplace itself, Laplace function of t domain is equal to integral of 0 to infinity of function of time domain exponential minus st dt. Laplace's relation has been able to resolve many problems of differential equations. What Sir Isaac Newton could not do, Sir Laplace was able to resolve it using this relationship. It's a semi-infinitesimal cycle. So what happens is, if we are given a function, find Laplace function of a. Laplace a, as it were, is simply integral O to infinity of a exponent minus st differential t. What happens is that the Laplace value given will be induced into this general Laplace function formula. This is Laplace. S means Laplace. So since a is a constant, we get it out to be a integral O to infinity of exponent minus st differential t. Our usual integration comes to play to give you a dot negative reciprocal of s of exponent minus st from point of origin to infinity. When this is done, we now introduce the substitute of the definite value, and that gives us minus a over s into element of infinity minus exponent 0, as this infinity replaces t and also affect s, 0 replaces t and affect s. So as a definite integral, when multiplied, you have minus a divided by s, bracket 0 minus 1. When expanded, you have a over s. This is often found in the Laplace table. This is often found in the Laplace table. Also, progressively, if we are to get others, like Laplace transform of exponential minus at, or precisely, you can call it Laplace of at. Let's remove the minus. What you do is to integrate 0 to infinity of exponent at dot exponent minus st differential t. It is the differential, the dt, that metamorphoses into the integrals of t concepts. All other functions there are seen as a constant, but we work with t as a derivative for the integration to manifest. So what do we have here? Firstly, we get the expansion, and the expansion gives us exponent minus into s minus a bracket t. That is collection of like terms. T is collected out. So via expansion, you get c. In course of integration too, we have minus reciprocal s minus a, that is here, the coefficient of t. Now exponent minus bracket s minus a t, limit 0 to infinity. So integration is key in Laplace transformation. So in all of this, when integrated and substituted, you have minus 1 over s minus a is exponent infinity minus exponent 0. So this gives us reciprocal of s minus a into 0 minus 1 as usual. And these are found 1 over s minus a. And from the Laplace table, we could see that this is a clear indication of the proof. On and on and on. Laplace function of t exponent n also is n factorial over s raised to power n plus 1. So these are observable concepts in Laplace transform. The proof sometimes is ambiguous, but it is pertinent to note that these are the direct substitutes we use from the formula translation. So on and on, we can look at joint functions in Laplace. For example, find the Laplace of t squared plus exponent minus 2t. How do we solve this? Laplace transform of t squared plus exponent minus 2t. Solution to this. You break the Laplace into two parts. Laplace of t squared plus Laplace of exponent minus 2t. When this is written, we'll go straight away with the formula relations, and this gives you 2 factorial divided by x raised to the power 2 plus 1, where the n is being replaced with 2 from the formula relation. Take note that exponent at already is giving us this relation. So exponent minus 2t will of course give us 1 over s plus 2. Why? The negative sign here will definitely affect this a to give us this. So furthermore, 2 factorial is 2. Final answer will be 2 divided by s cubed plus 1 over s plus 2. That is the answer for this Laplace problem. Trigonometrical functions are not left out in Laplace transformation. In trigonometrical function, Laplace transform of sine A, sine AT, from formula method, which we can derive over time, but as a quick data guide, Laplace of sine AT is A over s squared plus b squared. So if you are given Laplace of sine 4t to resolve, how do we do this? It's so simple. Let A become 4. So answer gives us 4 over s squared plus 4 squared. So you see, it is easy to resolve a Laplace transform working with the formula relation. The first question is purely algebraic. Now, this second question is trigonometrical in nature. So it is also a different thing altogether because of the transformation. Euler's logarithmic implication was used as exponent JAT is equal to cos AT plus J sine AT. This is key for the derivation of Laplace of sine AT. This is imaginary function, exponential imaginary function. If AT is equal to theta, this translation becomes exponent J theta. Exponent J theta is equal to cos theta itself plus J sine theta. So, of course, it is quite a simple proof to work with, but we will not look at the proof at the moment. Some other time we look at the proof, how we arrive at sine AT equal to A over s squared plus A squared. So again, Laplace transform of cos minus 5t. If we are expected to work on this, what do we do? What is Laplace of cos AT? Laplace of cos AT. Laplace cos AT is equal to s over s squared plus a squared. This is the Laplace transform for cos AT. So if we are given this to resolve, it's quite simple. All we do is formula translation. And that simply gives us Laplace of cos minus 5t is equal to s over s squared plus minus 5 all squared. That gives us s over s squared plus 25. So Laplace transform is very fundamental in engineering. The target of Laplace was to use it in resolving differential equation problems. when we have the second order differential equation, the likes of y prime prime plus y prime equal to cos at. We can use Laplace transform to solve this problem. A lot of dynamical models and other mathematical models can be resolved easily with Laplace transformation, but the fundamentals of Laplace is quite key, because without this fundamental, we will not go into the derivative function. The derivative function is what metamorphoses into its application. The likes of characteristics equation, the likes of Skydarvas equation, and the aeroplane equation.